This video is going to talk a little bit about what we call trigonometric functions or trigonometric vectors. And a trigonometric vector is basically just another way to write a vector so that we can represent the magnitude and the direction a little bit more exactly. Right? Again, it's kind of shaping a vector by talking about that magnitude and direction. So to talk about shaping a vector, we've done this before. A unit vector is sort of a reshaping of a vector as well. Remember that a unit vector is basically taking the magnitude of a vector. So let's say the magnitude of vector v here, which would be the square root, again, of 8 squared plus negative 20 squared, basically the square root of 464, which I know previously is 16 times 29, or basically 4 root 29. And now what I'm going to do is take vector v, and I'm going to divide it by its own magnitude. We're going to reshape the vector. We're going to sort of re-lengthen it, right? Now, we're not really reshaping it a lot. We're just taking 8 and dividing that by 4 root 29. And then at the same time, I'm going to take negative 20 and divide that by 4 root 29. Well, if I take 8 divided by 4, that's 2 over root 29. Let's write that so we can actually read it here. 2 over the square root of 29, which again, you could also rationalize, right? Multiply that root 29 up to the top. And also negative 5, right? Negative 20 divided by 4 over the square root of 29. And now we've got a vector that would be of length 1, right? The magnitude of that vector would be of length 1. Well, in that case, if we can shrink a vector to be of length 1, if we multiply that vector by something, right? If we multiply, we should be able to stretch a vector as well, right? Any vector can be represented, again, as a sum of its two component vectors, and it can also be a multiple or a stretch of another vector. So if I want a vector of length 10, right, I want magnitude of vector v to be 10, but in the direction, right, of the given vector, in the same direction as u, what I would really want to do is take vector u, I'm going to divide it by its own magnitude, but then I'm going to multiply that by 10. I'm going to shrink it to be of length 1, but then I'm going to multiply by 10 and force it to be of length 10. So in that case, again, we first need to know the magnitude of vector u, which would be the square root of 2 squared plus negative 3 squared, or basically the square root of 13. So I can now say that that would be 2 divided by root 13, right? I minus 3 divided by root 13, j, right? Horizontal and vertical components. But then I'm going to multiply that by 10. So basically if we had 20 root 13 over 13, right? I'm going to go and rationalize, times I minus 30 root 13 over 13 j, and I double check the magnitude of that vector. Trust me when I say we shrunk it to be of length 1 and then we stretched it to be of length 10. The magnitude of this vector should be 10 units long, only in the direction, right, of the same direction of u. It's in proportion to negative 3, right, in that direction. Now, if we can shrink a vector or stretch a vector, what we can do is take a unit vector then, right, and we can make it into a trig vector. Think about your unit circle, right, as we would normally write it over here. If A were, or A and B, if that magnitude were of length 1 right there, right, on our graph, well, the horizontal and vertical components, A and B, very simply represent a vector of length 1. And if we remember, if we take those, and cosine and sine, often on our unit circle, represented the x-coordinate and the y-coordinate. Well, if I multiply those by I and j, or if I just leave those in sort of that component form, remember that on a unit circle, right, cosine of theta, comma sine of theta represented every point, right, around our unit circle. So in that case, if I take a vector cosine sine and I multiply by a magnitude for vector v, I should get a vector of the length that I want, but in the direction, right, theta, in the direction angle that I want, right? Very simply here. We would call this angle theta. So find the direction angle and magnitude of v. Well, we know how to find the magnitude. The magnitude would be, again, for vector v, the square root of 3 squared plus negative 4 squared, or basically the square root of 9 plus 16 is the square root of 25, so magnitude 5. Now to find the direction, on the other hand, we sort of need to represent our side lengths, right? These are going to be the sides of the triangle as 3 and negative 4. But now realize that, again, if that's going to be our vector, magnitude of v times cosine sine, what we can say, right? Remember that tangent is equal to the sine over the cosine. And if we took those magnitudes and we sort of canceled them away in here, well, basically the direction angle theta is really the tangent of theta equals sine of theta over cosine of theta. Well, very simply, we can say that tangent of theta is b over a, right? Again, cosine being sine being our b value, and cosine being our a value, right, on our unit circle. Sine always represented the y-coordinate, the up and down, right, the vertical component, and cosine again representing our horizontal component. So if you want to find the direction of a vector v, what we can say is that the tangent of theta would be equal to b over a. So if we take the inverse tangent of negative 4/3, this should get us our direction vector, right, or our direction angle. So let's go ahead and do that. Let's hop onto our calculator here. I'm just going to clear off what's on here. Now notice we're in radian mode right now, and that's perfectly fine. Let's go ahead and do this in radians. So we're going to say the inverse tangent, right, of negative 4/3. And I changed my mind. Let's actually go ahead and do this in degree mode. You can do it either way. Vectors can be represented with either radians or degrees. But I'm going to go ahead and go in degree mode. And the inverse tangent of negative 4/3 is negative 53.130 degrees. So approximately negative 53.130 degrees. Now the one problem I would have with that is that, notice our vector again is going 3 to the right and down 4, so it is going here. But if you wanted to, you could add 360 degrees to that if you wanted to represent the angle maybe in a positive fashion. But otherwise, again, to write the trig form of a vector, right, kind of like we have up here, I just need to take my magnitude and multiply it by the cosine of negative 53.130, comma, the sine of negative 53.130. And I would be willing to bet you, if we took that and we went back to our calculator, if I said 5, the cosine of my angle, again, notice it's rounded, but notice how we get that answer of exactly 3 there, right? And I think my calculator did a little bit of rounding there. Or if I said 5, the sine, again, of that given angle, notice we get our negative 4 back, right? 5 times the cosine of the angle was exactly what our component form was, right, of 3. And 5 times the sine of the angle, exactly negative 4. So again, this is the trig form, right, representing in terms of, rather than horizontal and vertical components, we're representing it in terms of magnitude and that direction angle, right, magnitude and angle. Let's practice doing that one more time. So let's take this vector here and let's represent the vector, right, the vector given, so negative 2, 5, as a linear combination. So realize we want to end up in i's and j's in trig form. So again, in terms of theta and r. Now r would kind of like be saying the radius here, right? R is in like our magnitude r, right? The length from origin, right, outwards. We call that r. So if ever they talk about theta and r, right, we're really just talking about our components here, our direction and our magnitude r. Well, first things first, let's go ahead and find the magnitude. So we're going to say the magnitude of this vector, and let's just give it a name. I'm just going to call it vector v. So the magnitude of vector v will be equal to the square root of -2 squared plus 5 squared. That's the square root of 4 plus 25 equals the square root of 29. Then the tangent, remember, of theta is equal to b over a, or 5 over -2. I'm going to go ahead and let my calculator do the work on that one, but that's going to be the inverse tangent, right, of 5 over -2, or theta would be equal to, and again, I'm going to hop on the calculator here, the inverse tangent of 5 divided by -2, and we get a -68.199 degrees. -68.199 degrees. Now, I have a slight problem with that one, only in the fact that if we did graph out our vector, we went left 2 units and up 5 units. Our vector should be traveling up to the left, and -68 degrees travels down into quadrant 4. But remember that tangents are also negative, right? -5/2 there, up in quadrant 2. So what I'm actually going to do is go ahead and add 180 degrees onto this, right? So let's hop back to our calculator. Let's say plus 180, because I want to make sure that my vector travels in the correct direction. So that's really 111.801. 111.801 degrees. So if I want to write out my trig form, again, with i's and j's, it's going to be the square root of 29 times the cosine of 111.801 degrees. I, right? And notice you can write that I. Oftentimes you'd put a dot and then put the vector. Shortcut way of doing that is just sort of making your vector symbol into the dot above the I there. Then I'm going to add on, again, square root of 29 times the sine of 111.801 degrees. Again, I would have written it in one smooth line, but I kind of ran out of room there. But notice, again, we've represented our vector, our horizontal component, in terms of the cosine of the angle times the magnitude, and our vertical component in terms of the sine. Oops, and I forgot the j on the end there. If we're going to represent with i's and j's, we better have j in there. So again, add on j here. Okay. But again, j times the sine of the direction times the magnitude should stretch that vector correctly. If you have any questions about trig form of a vector, make sure you talk to your teacher. Otherwise, have a great day.